Yes, Siddharth. Last day we have discussed.
Yes, sir.
Last topic is
Rotational Raman spectrum.
rotational Raman.
Yes.
Rotational Raman is completed. Nuclear spin
Yes,
reaction.
sir. Yes, sir. Yes, sir.
Today is
Nuclear
vibration.
spin.
Yes, no. Okay, let
Yes,
me
sir.
start vibration Raman spectrum.
Yes, sir.
What is vibration Raman spectrum?
Mm, yes, sir. So in vibrational Raman spectrum, uh, we study the how the vibration, the change in polarizability of molecule occurs, and from this, the scattering of light or sun occurs, and we get a spectrum of the vibrational Raman spectrum. So for a triatomic molecule H2O, the normal modes of vibrations are four, but of them, one is symmetric stretch, one is asymmetric stretch, and two are degenerate bending. So if I draw the change in polarizability of each of these, so I can understand how they are they are Raman active. So for symmetric stretching, that I define as V1, and bending V2, and asymmetric stretch as V3. So for V1, the change in polarizability, I explain the change in polarizability by via the polarizability ellipsoid, that is like this for normal H2O, and in symmetric stretch extension. So this is the symmetric stretch extension. As the bond length increases, the polarizability ellipsoid shrinks, and as the bond length decreases via contraction or expansion, yes, so bond length decreases, so the polarizability ellipsoid increases in size. So this is the symmetric stretch, that's V1 of H2O molecule. So as we can see, there is change in polarizability ellipsoid. So this particular symmetric vibration is Raman active, vibrational Raman active. Now I am talking about the bending vibration. So for bending, here bond angle changes. So this is the normal mode of vibration. So for the polarizability ellipsoid is again this, and with here the bond angle increases by symmetric the bending vibration. So the polarizable ellipsoid becomes the shape of polarizable ellipsoid become strings like this. And as the bond angle decreases like this, so the polarizable ellipsoid becomes more like this. So here also I can see the change in bond angle uh, results the change in polarizability ellipsoid. So here also this mode of vibration is Raman active. Now coming to the asymmetric, that is the V3 asymmetric stage. So oxygen, this hydrogen, and this hydrogen, this hydrogen, and hydrogen, and this hydrogen. So polarizable ellipsoid will be for normal H2 molecule like this. For this molecule, the direction will change. So that direction will be this direction, and for this polarizability ellipsoid will be in this direction. So as we can see, with changing the polarizability ellipsoid, the molecular polarizability of H2O for new1, V1, V2, and V3, the three types of vibration, and the polarizability changes with this vibration. So these three are rotational vibrational Raman active. Now I am taking another example. That molecule has a center of symmetry, and that is CO2. Again, CO2, CO, and this, and so for again this is the normal CO2, and this is the compressed. So the polarizable ellipsoid will be in large size. This will be small size. So this is symmetric stage V1 will be V2. So for this bending vibration, polarizability ellipsoid will be this, and V3, that is asymmetric stage. So C4. So this is, and these are more or less same. So these are the polarizability ellipsoid. So from this polarizability ellipsoid, we can tell that all of the three vibration motion is Raman active, but in reality, only the symmetric stage is Raman active, but not the bending, or neither the bending nor the asymmetric stage. This can be explained by via the graph. So I am now drawing the graphs where alpha is polarizability and xi is displacement, and this displacement, whether for stretching, is extension or compression, that is positive, compression, that is negative, and for bending it is change in bond angle, whether in positive or in negative. So if I draw the graph. So this is 0, this is plus xi, this is minus xi. So for symmetric stretch, the graph is like this. For bending, it is increased by two sides in similar way. So this is the near the equilibrium vibration, and this increases both sides similar way, and this is alpha and this is plus xi. And for asymmetric stretch, the graph will be like this. So from the three graphs, we can see that near the equilibrium position, or where xi equals to 0, there is no displacement. So near this position, there is a certain change of slope for symmetric stretch. So in this place, dxi by d alpha is not equal to 0, and this is the condition for a molecule to be vibrational Raman active. But in case of symmetric bending or bending vibration, so in here near the equilibrium position, d alpha by d xi equals to 0. This is the flattened curve here. And for the asymmetric stretch, here also d alpha by d xi is equal to 0. So as these two are, the slope here near the equilibrium position is 0, these two bending and asymmetric vibrations are vibrational inactive. So from here we can understand the symmetric stretch is vibrational Raman active, but not the other two.
Yes.
Now if I solve this in mathematically, so energy V is equal to V plus half omega E minus V plus half square omega E x. This is the vibrational energy of the vibration, and the selection rule for a molecule to be rotational vibrational Raman active, its delta G is equal to 0, plus minus 1, plus minus 2, plus minus 3. But we only consider the first three, as here intensity becomes very low and undetectable in our spectrum. So when delta V equal to 0, that corresponds to our Rayleigh line or new excited line, and no, delta V equal to 0. So here EV equal to delta E, delta E will be equal to V equal to 0 to V equal to 1. That is our fundamental vibration. So here the energy will be 3 by 2 omega E minus 9 by omega E minus 1 by 2 omega E plus 1 by 4 omega E xc. So solving this, this will be omega E minus 2 omega E Xc, and this is the fundamental vibration that mainly we concern about in vibrational Raman spectrum. So if I draw the graph, draw the spectrum, this will be the Rayleigh line or the excited line, that is the molecule takes of energy. So this is 0, and here will be the Stokes line and anti-Stokes line here, and intensity of the anti-Stokes line is very low than the Stokes line, as here the energy change is V equal to 0 to V equal to 1, as the molecule absorb the radiation, absorption takes place, and this in this area V equal to 1 to V equal to 0, and because we know the from V equal to 1 the population in vibrational level V equal to 1 is very low. From the calculation we saw that the population and V equal to 1 level is 0.008 of V equal to 0, so very low population. So this will the population is very low, so the intensity of the lines will be very low. So we generally do not discuss the anti-Stokes lines here. So, and this is the delta I is the fundamental delta I here. So this will be the spectrum for vibrational Raman spectrum.
Yes. Yes. Right. Good. What is a rule of mutual exclusion principle in vibration Raman spectra? What are the uses of these one? Main application and uses?
Yes, sir. As I was previously saying, for CO2, the molecule which has center of symmetry. So for this type of molecule which has center of symmetry, the vibrations that are IR active are Raman inactive, and vice versa. That is, the vibrations that are Raman active will be IR inactive. This rule of mutual exclusion only applies for the molecules that possess center of symmetry. So we see that for CO2 there are the type of vibration: symmetric stretch, asymmetric stretch, and bending. So, and for symmetric stretch there is no change in the dipole moment. So this stretching vibration is IR inactive, as there is no change in the dipole moment during vibration. On the other hand, as I was drawing, there is the change in molecular polarizability, and d alpha by d psi not equal to 0 here. So this particular symmetric stretch is Raman active. And as for asymmetric stretch, here change in dipole moment occurs. Here also change in dipole moment occurs during vibration. So these are IR inactive, IR active. But these two are, as I was saying, d alpha by d psi equals to 0 here. So these are Raman inactive. So from this rule of mutual exclusion principle, if we see for a molecule which has uh, higher active vibration that are Raman inactive for all the vibrations and the vice versa. So we can say that the molecule possesses a center of symmetry, and we can draw the skeletal of the molecule like we can draw CO2 like this. On the other hand, if the molecule in a that is and both. So we can definitely say the molecule does not possess center of symmetry, and so the molecule does not look like this. So these are the thing that we can understand from the rule of mutual exclusion.
Yes, yes, rule of exclusion main basic principle is rule of mutual exclusion does not apply SO2 molecules. Why? Apply in BF3,
Yes, sir.
H2O, CO2, SO2. Why?
See, sir, the molecule SO2, uh, the rule of mutual exclusion applied for only molecules those don't have center of symmetry. And for this type of molecules, the higher active modes are Raman inactive. But for the SO2 molecules, the molecule looks like this. So in this molecule, there is no center of symmetry. So it cannot follow the rule of mutual exclusion principle.
Yeah,
And from the iron,
non-centrosymmetry present in SO2 molecules. Yes,
yes,
no.
sir, yes, sir, no center of symmetry present.
Yes. Next is question is what the difference between Raman and IR? Explain. 4-5 point.
Raman and IR, yes, sir. IR, Raman. So in Raman spectroscopy, IR spectroscopy, we saw the uh, molecule molecule interact with the radiation, interact with radiation. Of infrared IR, yes, and here the molecule radiation, and we study the scatter radiation, the molecule, the radiation that is scattered by the molecule. Then for IR the molecule there is there must have change in dipole moment in the molecule during vibration. On the other hand, there is uh, no such change in dipole moment required. Rather, here the change in molecular polarizability is required to be Raman active. Here, the homonuclear diatomic molecules are iron inactive because they do not possess any dipole moment during the vibration, during the change of vibration. And in this case, homonuclear diatomic molecules are Raman active, whereas the spherical tops molecules are Raman inactive, as there are no appreciable change in the spherical polarizability ellipsoid of the spherical top molecules.
Yes. Yes, good. Next point is what the difference between Raman and fluorescence? 4-5 point बताइए.
Fluorescence. तो फ्लोरोसेंस अभी पढ़ा नहीं, तो वो स्टडी नहीं किया. तो फ्लोरोसेंस वो तो फोटो केमिस्ट्री में रहता है.
फोटो में आ जाता है, लेकिन यूजेस है ना, स्पेक्ट्रम लाइंस लाइंस इंस्पेक्ट करते हैं. फ्लोरोसेंस फॉस्फोरेंस रमन में यूज होता है ना. फ्लोरोसेंस और फॉस्फोरेंस पोलराइज्ड लाइट के अकॉर्डिंग
वो
यूज होते
पढ़ना
हैं.
पड़ेगा. अच्छा सर, ओके ओके सर, वो पढ़ना पड़ेगा फिर
यस यस,
तो
कोई बात नहीं. नेक्स्ट टॉपिक हम डिस्कस करते हैं इलेक्ट्रॉनिक स्पेक्ट्रोस्कोपी. व्हाट द मेन एप्लीकेशन ऑफ इलेक्ट्रॉनिक स्पेक्ट्रोस्कोपी?
Yes, sir. So, in electronic spectroscopy, so the main use of electronic spectroscopy that it is applicable for any kind of molecule, homonuclear or heteronuclear, any kind of molecule. So, electronic spectroscopy. So, for every type of molecule, this electronic spectroscopy is applicable, and from this electronic spectroscopy we can deduce the value of d0 double dash, that is the ground state dissociation energy of a molecule So this is the main application that the electronic spectroscopy have.
Yes. What the range of UV visible light, UV and visible in electronic?
The range, sir, under 3000 nanometer, but I do not know the range properly this time, but it is under 300 nanometer. Can you give me the range, sir?
Yes, UV range is 200 to 390 nanometer, and visible is 390 या 400 to 780. 390 to 780.
478. Oh, okay, sir.
Is what the
200.
source of a UV visible spectroscopy?
Source.
Yes.
Sorry, sir.
Yes.
पढ़ना पड़ेगा, sir.
Yes. UV source is a hydrogen deuterium discharge lamp. And visible source is tungsten filament.
Hydrogen deuterium
Hydrogen deuterium
discharge lamp.
discharge lamp UV. और visible tungsten filament.
Visible tungsten. Visible tungsten. Okay.
Yes, first of all is discuss is what is Lambert-Beer law in electronic spectrum. Explain briefly.
Beer-Lambert law. Okay. So
Yes.
Beer-Lambert law mainly tells us about the absorbance of a molecule. That is, absorbance is proportional to the length of uh, the length, and it is directly proportional to the concentration of the uh, solution used. So together, this is written as A is equal to epsilon C, where epsilon is molar, not molar, this is optical density.
Yes.
Absorbance is written as log I0 by I, and again I by I0, that that is called transmittance. So A is equal to negative log T.
Yes. What the uses of uses Beer-Lambert law?
Yes, sir. So from the Beer-Lambert law, we can if here this is a cuvette of length L, and here is concentration C of the solution used. If radiation pass through this, so initial intensity I0, after it is I, so we can calculate transmittance by I by I0, or absorbance by log I0 by I, and absorbance is a additive quantity. So additive. So if a series of solution is placed like this, so from each of the, by adding each absorbance, and whether the transmitter is multiplicative property, so by adding this, or by taking each one's transmittance value and multiplying, we can get the total transmittance or total absorbance of the molecule of the molecule, or the molecule of the solution.
What the limitation of Beer-Lambert law?
Limitations. सर लिमिटेशंस याद नहीं है सर। मैं बोल रहा था कि इलेक्ट्रॉनिक स्पेक्ट्रोस्कोपी कौन से बुक से पढूं तो ज्यादा अच्छा रहेगा?
Ian Vanwell.
बैनवेल?
Yes.
तो बैनवेल के अलावा, बैनवेल तो पढ़ रहा हूँ, लेकिन बैनवेल के अलावा अगर कुछ और, मतलब ये बी लंबट लो, ये सब पढ़ना हो तो?
Beer-Lambert law Vanwell में दिया है ना, फिजिकल स्पेक्ट्रो है ना, फिजिकल स्पेक्ट्रो Vanwell में
यस सर।
है। ऑर्गेनिक है पाविया, आर के शर्मा की एक बुक भी
यस सर।
आती है, सिल्वर स्टील भी आती है, बहुत सारी बुकें आती हैं, लेकिन टाइम नहीं है ना इतना।
यस सर।
पाविया उससे पढ़ लीजिए, वैनवेल इज सफिशिएंट, सब कुछ दिया तो वैनवेल में, ये लेमर्ड लॉ,
जी सर। जी सर।
एग्जाम्पल सब कुछ है। लिमिटेशन नहीं होती है तो लिमिटेशन आप गूगल पे सर्च कर सकते। लिमिटेशन ऑफ बीएल लॉ,
जी
देखो
सर।
सॉल्यूशन शुड बी, बता देता हूँ, लिमिटेशन है सॉल्यूशन शुड बी डाइल्यूट। यस। नंबर 2
हाँ, डायल्यूट
पॉइंट,
सॉल्यूशन के लिए
yes, temperature must be kept constant during
कांस्टेंट।
experiment. Number third point, there should be no chemical reaction in the solution. Yes, no.
यस सर।
थ्री लिमिटेशंस। तो इसकी जो एप्लीकेशन थे बीएल लैम्बर्ट लॉ के, जैसे नंबर एक मेजर पॉइंट बता देता हूँ, डिटर्मिनेशन ऑफ मॉलिक्यूलर
यस सर।
वेट ऑफ गिवन सॉल्यूट। नंबर 2, डिटर्मिनेशन ऑफ कंसंट्रेशन ऑफ गिवन सॉल्यूशन अननोन। two main applications. Yes, no. Next point is discussing Frank-Condon principle. What is Frank-Condon principle in electronic spectra? Explain.
Yes, sir.
Explain.
So, Frank-Condon principle tells us about the transition or the type of transition that will occur from one vibronic state to another. Um, so the statement states that uh, when electronic transition take place, so the transition is so fast that the molecule in the upper or and the ground state do not change their vibration during the transition. So if I draw an electronic state, this, and there are three type of conditions. First, where R equilibrium of ground state equal to R equilibrium of excited state. So in this case, these two states will be exactly at the right, like this. R equilibrium, this is energy, and this is internuclear distance. So V equal to 0, 1, and this. So according to Frank-Condon principle, the transition will take place from this state to this state via a vertical transition, not like this. The transition will be like so the transition will be this, like vertical transition, not like this, that this, not this type of transitions will be allowed, or this will not, this type of transition will happen, and the only transition happened is the transition from the ground state to excited state. This is the Frank-Condon principle.
Yes, Frank-Condon principles is which node is absent, which node is present, and what the difference between our transition in low intense, more intense. Explain.
Yes, sir. So in transitions, in in vibronic electronic transition, is so 0, 1, 2, 3. So V equal to 0 to 0,